Okay, so good evening everyone. I am Shivani Tok and I welcome you all for the week 8 tutorial for this course that is Digital Signal Processing and its application. So like every week I'll first recap the week 8 content and then I'll do some questions which are related to this content. So let's start with the recap of week 8 content. So in week 8 basically we started with Butterworth filter like poles and its transfer function. So let me just write down these things for our reference, or let me just add a page and let me write it down. So for Butterworth filter, what do we have? We have order n, which will be at least equal to ceiling of half log d2 by d1 upon log omega s by omega p. This is the first thing. Then this omega c, that is the cutoff frequency, this lies between omega s upon d2 to the power 1 by 2n and greater than or equal to omega p upon d1 to the power 1 by 2n. Then the poles of this filter are sk's, which is equal to omega c into e power j 2k plus 1 plus n upon 2n multiplied by pi, and its transfer function h of s, or h analog of s, is basically equal to omega c to the power n upon product of k running from 1 to capital N omega s minus sk. This is all about what is your Butterworth filter. After that we looked at this Chebyshev filter, and in Chebyshev filter again we had this epsilon and order. So we found out that this epsilon is less than or equal to plus under root d1, and we said that we should choose the value as d1, under root d1. Then we had this formula n to be at least equal to ceiling function cos h inverse under root of d2 by d1 upon cos h inverse omega s by omega p and ceiling function. So this was Chebyshev filter. We looked at its poles also, and we looked at these things. After that we had analog domain transformation. So we said that if we know how to design a low pass filter, that information is sufficient and we can do analog domain transformation to construct other types of filters. So in this week we looked at high pass filter and band pass filter. So for high pass filter, this transformation was, we use another color yeah. For high pass filter, this transformation was SL to be replaced by omega p by s, which means that omega L should be replaced by omega p by omega. And same thing we did for band pass filter also. So we had for band pass filter, we had omega L to be replaced by omega square minus omega naught square upon b omega, and we found out that this omega naught square is omega p1 into omega p2, and omega this b corresponds to bandwidth, which is omega p2 minus omega p1. Okay, and this omega ls is minimum of magnitude of omega ls1 comma magnitude of omega L is 2. So this was all what was discussed in this particular week. If you have any questions, just let me know. Otherwise, we'll move ahead with the questions that I want to cover today. Yeah, another thing is this SL has to be replaced as so this is all that was discussed today. Okay. Any questions? Okay. If there are no questions, then let me just move on to the questions that I have planned to cover today. So here the first question is, suppose we are designing a discrete time low pass filter with following specifications. So the passband edge FP is 4 kilohertz and 0.8 dB tolerance is there. Then stop band edge is Fs equal to 4.5 kilohertz and we have 50 dB attenuation, and we have sampling frequency Fsam as 22 kilohertz. So it says that let h of omega denote the filter response if in passband this is satisfied, that is this magnitude response is between A and B, then we need to figure out what is this A and B. Okay, so in passband, so if we are having this variation in passband, this directly indicates the consideration of this tolerance. So now what we are given is tolerance in passband is 0.8 dB. Okay, so now this is given in dB. Now if we have in passband, what do we intend to have? This we intend to have, but and what this in dB scale, or rather the gain in dB scale will be equal to 0. This is intended thing. But what we will have is, we'll have a plus minus deviation of 0.8 dB. Okay. So therefore, this gain, that is 20 log magnitude of h of omega, should lie between 0.8 dB and minus 0.8 dB. So now I can do some
Madam,
yeah,
can we call 0.8 dB as alpha P,
alpha
maximum allowed attenuation in the passband?
alpha P. What is alpha?
Alpha means attenuation, maximum allowed attenuation in the passband. Can't we call it?
Yes.
There, there should not be any attenuation, but there is attenuation. It should not exceed 0.8 dB.
Yes, this is not attenuation. This is like some deviation that you can have. This is not attenuation. How much you can go up and below a particular level.
Madam, it is attenuation only, no? 0.8 dB.
What do you mean by
There,
attenuation?
yeah. In the passband, I don't want any attenuation. I want to pass the signal as it is.
Huh.
But but there is attenuation. It should not exceed zero point 0.8 dB. That's what I am telling.
Okay. Yes.
Yeah.
So then what I can have is, I can write this as 0.8 by 20 less than or equal to log. Since it's a dB thing, it will be log to the base 10. Okay, and then I can write this as 10 to the power minus 0.8 by 20 less than or equal to magnitude of h of omega less than or equal to 10 to the power 0.8 by 20. So this comes out to be, if you use calculators, this comes out to be something like this. This is the final answer that we wanted to find out. Simple question. Any queries here? Okay. If there are no queries, then let me move on to the next question. So the second question says that in question 1, find the passband edge and transition band for the equivalent analog low pass filter. Okay, so what do we need to find out? We need to find passband edge and transition band for equivalent analog low pass filter. So for this thing has to be done in 2 steps. So if you observe, the specifications given to us here are in analog domain, but or the very basic specifications that are given to us. So these specifications are an analog domain, but these are not the thing that we shall use because tan is a non-linear function. So we will have some sort of pre-warping coming up. So for that, what we will do is step 1 will be normalize given specifications, and step 2 will be use bilinear transform to get equivalent analog filter specifications. Okay, so this is what we have. Okay, yeah, fine. So let's start with the step 1. Step 1 is normalize specs. Okay. Now what is given to us? We have passband edge as 0.4 kilohertz, stopband edge as 4.5 kilohertz, and sampling frequency as 22 kilohertz. Okay, so let me just write it here. So we have passband edge. So let me do it for passband edge. So here FP is given to us as 4 kilohertz, and we have sampling frequency as 22 kilohertz. So therefore normalized thing will be omega p as 2 pi fp upon f sampling frequency. This is 2 pi into 4 into 10 raised to 3 divided by 22 into 10 to the power 3. This gets cancelled. So this comes out to be 4 pi by 22. So this is my normalized thing. And similarly, I'll have it for stop bandage.
Four five by 11, madam.
Sorry.
4 5.
Yeah, thanks. Let me just do this on next page. Yeah. Next, we'll do the same thing for stop bandage. So in stop bandage, what is given to us is Fs is 4.5 kilohertz, and we have the same sampling frequency, that is Fsam, which is 22 kilohertz. So therefore this omega s, that is the normalized frequency, will be 2 pi Fs upon Fsam, which comes out to be 2 pi into 4.5 into 10 raised to 3 divided by 22 into 10 raised to 3. This will get cancelled, and 4.5 into 2 is 9, so we have 9 pi by 22. So now what do we have? We have this omega p, and we have this omega s with us. So if we have these two things, we can easily now move on to the next step in this process. So now we can go with step 2, which is bilinear transform. Okay, so we have this thing here. So let us first do it for pass bandage. So for pass bandage, we had omega p, which came out to be 2 pi by 11, which means that capital omega p will be tan of omega p by 2. One second, this is 4 pi by 11, sorry. So this is equal to tan of two pi by 11, and this is equal to 0.6427. You can find it out by using your calculators. Then for omega s, that is stop bandage, this omega s had come out as 9 pi by 22, which implies that capital omega s will be tan of omega s by 2, which comes out to be tan of 9 pi by 44, which comes out to be 0.7486. And what we wanted to find out, we wanted to find out transition band also, or transition width. So this transition band is omega s minus omega p, which is equal to 0.7486 minus 0.6427, and this comes out to be 0.1059. Is it clear?
Madam, no units, transition band.
No, there will be units, na, radians per second, everywhere radians per second.
Okay.
It's angular frequency, everywhere radians per
Yeah.
second are the units.
Okay.
Yeah. This is radians per second. This is also radians per second. It's not a ratio, sir. It's a subtraction. So your units will be preserved.
Okay, madam.
Yeah.
Okay.
Any other questions? Okay. If there are no questions, then let me just move on to the next question. So it says that any analog Chebyshev filter with parameter n, epsilon and omega p is designed. Suppose we have another filter with passband tolerance delta prime 1 less than delta 1, where delta 1 is passband tolerance of the original filter, and if n prime, epsilon prime and omega p is the new filter's parameters, which of the following is true? So we have these four options, and what are we given is, so we have a filter 1 with parameters order as n, epsilon and passband edge as omega p, and we have filter 2 with parameters n prime, epsilon prime and omega p, and for this we have a passband tolerance as delta 1, and for this we have passband tolerance of delta 1 prime, and another thing is the stopband tolerance for both of them is same. Okay, so we need to find the relation between these two quantities and these two quantities. Okay, so let us try to do that. So for that, let us first try to figure out what is the relation between epsilon and epsilon prime. Okay, so if we know that epsilon is less than or equal to under root d1, and epsilon prime will be less than or equal to under root d1 prime. Okay, and if we are setting up the best possible value of epsilon and epsilon prime, so we can set epsilon as under root d1 and epsilon prime as under root d1 prime. Now what is this d1? This d1 is by definition 1 upon 1 minus delta 1 square minus 1, and this d1 prime is equal to 1 upon 1 minus delta 1 prime square minus 1. Now both of these, this and this, are function of delta 1 and delta 1 prime. And we have been given a relation between delta 1 and delta 1 prime. We know that this delta 1 prime is less than delta 1. So what we know that delta 1 prime is less than delta 1. This is the knowledge we have. Now what we will do is, we will have this right. Let me do step by step. So if I multiply it on both the sides, then this inequality will get reversed. If I add 1 on both the sides, nothing will change. Now if I square on both sides, still nothing will change. Then what I can do is, I can take a reciprocal, so it will be 1 upon delta 1 prime square will be less than 1 upon 1 minus delta 1 square, and now if I subtract minus 1 from both the sides, nothing will change. Now if you observe carefully, this thing here is d1 prime and this thing here is d1. So what we get is d1 prime is less than d1. So in similar way, I can write this, which means that epsilon prime should be less than epsilon. So this is what we are having. So what we have is epsilon prime is less than epsilon. So the possible options are these. Okay. Now we know the relation between these things. Now let us try to figure out what will happen for order. Now the formula for order is n should be greater than or equal to ceil of cos h inverse under root of d2 by d1 upon cos h inverse omega s upon omega p. Now this stop band and pass band edges for both the filters are same. So this is for n. In similar way, we'll have n prime, which is greater than or equal to under root of cos h inverse under root of d2 by d1 prime upon cos h inverse omega s upon omega p. Why do we have d2 here? We have d2 here because this delta 2, which is stop band tolerance. So what is d2? This d2 is basically 1 by delta 2 square minus 1. So this delta 2 is same for both the filters, which means that this d2 is also same for both the filters. Okay. If that is the case, now this is the relation that we are having. And if we go for the least possible value of order, I can just simply do this, or rather n upon n prime should be greater than or equal to, or what we can do is we can simply just focus on this factor here. Let us consider this factor here. Or to be specific, this and this are also constant. The only term that changes is this and this. So let's focus on cos h, or rather let me write it properly. Consider cos h inverse of under root of d2 by d1 and cos h inverse of under root of d2 by d1 prime. Now we had obtained some relation here for d1. So we found out that d1 prime is less than d1. So we have d1 prime as less than d1, d, and we also said that we have this quantity. I can take a reciprocal, so it will be 1 over d should be greater than 1 upon d1, 1 over under root of d prime should be greater than 1 upon under root d 1, and I can just do multiply both sides by under root d2. Nothing should change. So this we have. Now another thing that we have here is, so if I take cos h inverse of on both the sides, the sign shouldn't change, because in this, for this d1 should be greater than d1 should be less than d2, which means that this ratio and this ratio both are greater than 1, and when this quantity is greater than 1, cos h inverse is monotonically increasing. So if I take cos h inverse on both the sides, this inequality shall remain same. So this we are having here. And now if I divide both the sides by a constant quantity like this, nothing should change. So if I have a ceiling here, then this thing should be n prime and this thing should be n. Now suppose this ratio is suppose this ratio is 4.2 and this ratio is 4.05. Okay, this is just an example, may not be true, just a simple example I am giving. Okay. Okay, so in both of these cases, n should take a value as 5, which means that even if this and this even if this is strictly greater than this quantity, but if 4 point something, or if this integer part of these two decimal things, if integer part of these two numbers, if those are same, then I'll have an order which is same in both the cases. So I can safely replace this inequality with a greater than or equal to sign if I apply a ceiling function. So what we can say is ceil of cos h inverse of under root of d2 by d1 prime upon cos h inverse of omega s upon omega p is greater than or equal to the root of ceiling of cos h inverse under root of d2 by d1 upon cos h inverse of omega s by omega p. And this thing here is my n prime, and this thing here is my n. So therefore we have this n prime greater than or equal to n. So we have this n prime greater than or equal to n. So this n prime is greater than or equal to n. So this is my final answer. Any questions? Is it clear? Any questions? If not, then let me move on to the next question. Okay. So the coming questions of whatever I have planned are basically all related to filter designing. So I'll take a simple small example for filter designing for band pass filter. And yeah, so this I shall take, and for all the remaining questions which I am having, I shall refer to only this particular data. Okay. So the data which we are having here is, the first thing that we have is that we are having a band limited signal which is limited to 160 kilohertz, and then they have given that passband and stop band tolerance, and this thing is 0.15 in magnitude, that is the stop band is 0 to 0.15 and passband is 0.85 to 1 in magnitude. Then what we have is sampling. So this band limited signal is sampled at 330 kilohertz. Then we are given that this pass band is from 85.7 kilohertz to 105.7 kilohertz, and the and the transition band is 4 kilohertz on either side of pass band. So let us try to visualize it, what exactly is happening. So let's say this is my frequency axis, and first thing that I can mark is my pass band. So my passband edge, first passband edge is FP1, which is 85.7 kilohertz. Let me write that this is in kilohertz. Then I have another passband edge, that is FP2. This is at 105.7 kilohertz. Then we have a transition width of 4 kilohertz on either side, like this. And then we have the stop band edges. So the first stop band edge is FS1, and this will have, so this FS1 will be equal to 85.7, that is FP1 minus 4 kilohertz. So this thing here is 81.7 kilohertz, and this thing here is FS2, and this thing here is FS2, and we can write it as this FS2 will be equal to FP2, that is 105.7 plus 4. So this thing here is 109.7 kilohertz. Okay, is this fine till this point? These are the specifications that are given to us, and this is for analog thing. So then we need to design a filter, and following questions will just take us slowly in designing the filter. Okay. Okay. So now let us go on to the question. So first thing that we need to do is we need to find the normalized specifications. So we have done a similar thing in previously also. So let us first find out the normalized specifications. Let's go step by step for this particular question. Okay, so we have this. First we need to find the normalized specifications. So we have, first let us do for passband edges. So also note that this F-SAM is 330 kilohertz. Okay. So therefore, the first passband edge is FP1, which is equal to 85.7 kilohertz, which implies that this omega P1 will be equal to 2 pi FP1 upon F-SAM, which is equal to 2 pi FP1 is 85.7 into 10 raised to 3 divided by 330 into 10 raised to 3. These things get cancelled, and this comes out to be 0.5194 pi. Another thing that we have is this FP2, which is equal to 105.7 kilohertz. Therefore, omega P2 is equal to 2 pi FP2 upon F-SAM, which comes out to be 2 pi into 105.7 upon sampling frequency is 330 kilohertz, this thing get cancelled. So what is left with us is 0.6406 pi. Okay, this we have. So this we have for passband edges. Next thing we can do is for stop band edges. So for stop band edges, the first stop band edge fs1 is equal to 81.7 kilohertz. So we have omega s1 as 2 pi fs1 upon fsam, which is equal to 2 pi into 81.7 kilohertz upon 330 kilohertz. If you use your calculators, this comes out to be 0.4952 pi. This was for the first stop band edge. Then we have the second stop band edge, which is fs2, which is equal to so this thing here so this fs2 here is 109.7 kilohertz. Therefore, this omega s2 is equal to 2 pi fs2 upon fsam, which is equal to 2 pi into 109.7 kilohertz upon 330 kilohertz, and this comes out to be 0.6648 pi. So what all do we have? So we have the normalized frequencies as omega p1 is equal to 0.5194 pi, this omega p2 as 0.6406 pi, omega s1 as 0.4952 pi, and omega s2 as 0.6648 pi. Okay. Okay, so this is what we are having here. Any questions in this part? Okay, if there are no questions, then let me go
Madam,
ahead. Yeah,
so what you got are the digital filter specifications.
yes, correct.
Okay.
So these are normalized specifications for discrete time filter.
Okay.
Yeah. Any other questions? Okay. If there are no questions, then let me move on to the next question. So anyway, if you be careful with this is the way you will be given your specifications, and you will be asked to design a digital filter or a discrete time filter. So the questions which are coming now are, you can consider it as steps to design that particular filter. So when you are given this particular information, the first step that you will do is to find this normalized specifications. After that, after finding these normalized specifications, you will find unnormalized or non-normalized specifications using the bilinear transform, and these specifications are basically, and these specifications will be for its equivalent filter, which we shall design using bilinear transform. So the thing is, we had analog specs, then we went to digital specs, and now we'll again go back to analog specs, but these analog specifications will correspond to these particular digital frequencies which we are having. And since tan is non-linear function, these analog specs which are given to us will not be same as what we'll get after applying this bilinear transformation. So this step, like getting this unnormalized specification step, is an important. You shouldn't directly start from this step, like you're given analog things, so directly go for analog filter designing. No, you should go for you should first go for design of you should first go for finding out the normalized specifications, and then you should again go back to the analog domain to design the equivalent analog filter. Please keep this thing in mind. It's subtle but important. This shouldn't cause any sort of confusion. Okay, so now this fifth question is, we need to find the non-normalized specs using the bilinear transform. So what we need to do is, we need to simply find this omega, which is tan of omega by 2. Okay, so again we'll have four things coming up here. So the first one, we have omega p1 as 0.5194 pi, which means capital omega p1 will be tan of 0.5194 pi by 2, and this comes out to be 1.0629. So these are rounded off to the fourth decimal place. Then we have omega p2, which is equal to 0.6406 pi, which implies that capital omega p2 will be tan of 0.6406 pi by 2, and this comes out to be 1.5790. Another thing you should keep in mind is, when you're doing this tan calculations, please keep your calculators in radian mode. If by mistake you keep it in degree mode, you will be screwed. Your answers will be totally wrong. So please be careful that your calculators have to be set in radians. In your final exam, you'll probably get a virtual calculator, so please be careful with it. Then we have omega s2. This thing will be equal to, so this we had found out as 0.4952 pi, which implies that capital omega s2 is equal to tan of 0.4952 pi by 2, and this comes out to be 0.9850. And omega s, sorry, this is not omega s2, this is omega s1, and we have omega s2 as 0.6648 pi, which implies that, sorry,
Madam,
yeah,
from omega S1, what we are getting is capital omega S1. You wrote it as S2.
thanks.
Okay.
And this omega s2 is equal to tan of 0.6648 pi divided by 2, and this comes out to be equal to 1.720. Okay, so now what we have the equivalent analog domain filters specifications. So specifically we have capital omega p1 as 1.0629, omega p2, that is capital omega p2, is 1.5790, omega s1 is 0.9850, and omega s2 is 1.7204. So these things are specs of equivalent bandpass filter in analog domain. Is it clear? Any questions here? Okay. If there are no questions, then this was a step 2 for this particular question or this particular filter designing process. Let's move on to the step 3. So the step 3 says that this band pass filter is then transformed to low pass filter using analog transform. If the passband edge of the equivalent low pass filter is taken to be 1, find the value of stop band edge. So what we have is we have this omega p set as 1, and if that is the case we need to find the stop band edge. So now we are having two stop band edges, and both of these stop band edges should give us omega ls1 and omega ls2, and we shall choose omega ls as minimum of these in magnitude. And how to find this omega ls? ls1 and 2. So this omega lsi, where this I belongs to 1 and 2. So this means that this I can take value as 1 or 2. So this thing is given as okay. So this thing here is given as omega si square minus omega naught square upon v omega si, where this v is omega p2 minus omega p1, and this omega naught square is omega p1 into omega p2. So if that is the case, then this b is equal to omega p1 omega p2 minus omega p1, and this is equal to, what was the omega p2 we had found out? Omega p2 was 1.5790. So this is 1.5790 minus omega p1 is 1.0629. So this is 1.0629, and this comes out to be 0.516. So this is our B. And another thing that we need to figure out is this omega naught square, which is omega p1 into omega p2, which comes out to be 1.5790 multiplied by 1.0629, and this comes out to be 1.6783. So if we have these values here, let us substitute back in the formula that we have. So therefore this omega lsi comes out to me omega si square minus omega naught square, which is 1.6783, divided by b. B is 0.5161 into omega si. Okay, this we have. So using this formula, let us first find out omega ls1, which is equal to omega s1 square minus 1.6783 divided by 0.5161 omega s1. This is equal to omega s1. What is its value? Its value is 0.9850. So this we have as 0.9850 to the power 2 minus 1.6783 upon 0.5161 into 0.9850. And this thing here comes out to be minus 1.3929. So this is my omega ls1. So this is the mapped frequency or transform frequency for one stop band edge. We have another stop band edge and we need to repeat the same process for another edge also. So for another edge we have omega ls2, which is equal to omega s2 square minus omega naught square, which is 1.6783 divided by 0.5161 omega s2. And this omega s2 we had found out as 1.7204. So this we can write as 1.7204 square minus 1.6783 divided by 0.5161 into 1.6783, and this thing here comes out to be 1.4433. You can use your calculators and just check it once. Okay, so we have this map frequencies for both the stop band edges, that is ls1 and ls2. Now what we said, we'll choose that. Yes sir.
Madam, at omega, just calculation, I think some error went.
Which calculation?
Just now, here.
Here.
It is not 1.6783. You have to substitute 1.7204. Omega S2. Put two different values, no? Here on, here on.
Yeah, thank you. Sorry. It should be one. I mistakenly substituted omega naught square. No. It should be 1.7024. If you solve this, this will give you this quantity. This quantity is correct. I mistakenly wrote here wrong. Thank you for pointing out. Okay, so now we have this omega ls1 and omega ls2, and therefore what we need to figure out is this omega ls, and we said that omega ls is equal to minimum of magnitude of omega ls1 comma magnitude of omega ls2. So this is equal to minimum of, what is magnitude of ls1? Magnitude of ls1 is 1.3929. So this is 1.3929, and this magnitude of ls2 is simply 1.4433, and this comes out to be 1.3929. So this omega ls is 1.3929. Okay. Any questions in this part? Are the steps for designing filter till this point clear?
Madam, can you show the sixth question again? Question.
Sixth one.
Sixth question, just to read out.
Yeah. So it says that if band pass filter is then transformed to low pass filter using analog transform, if
Okay.
pass band edge of equivalent low pass filter is taken to be 1, find the value of stop band edge.
Good. Okay, madam.
Okay? Yeah. Any other questions? Okay. So now we have the value of pass band edge, we have stop band edge, tolerance values are given to us. The next thing that remains is we need to figure out order of the filter. So next step is find the order of the Butterworth filter for given specification. So let's first do this thing for Butterworth filter and then we'll do the similar thing for Chebyschev filter. Okay, so now it's given that we need to find out the order of Butterworth filter for given specifications. So for Butterworth filter, the order n should be greater than or equal to ceiling of half into log of d2 by d1 upon log of omega s by omega p. So to be very specific, omega ls by omega lp. Okay. So now we know the value of this, we know the value of this. Another thing that we know from the given specifications is this delta 1 is equal to delta 2 is equal to 0.15. It's given. Now, what we don't know is the value of this d2 and this d1. Okay. So let us try to find that out. So what is d1? This d1 by definition is 1 upon 1 minus delta 1 square minus 1. So this will be equal to 1 upon 1 minus 0.15 square minus 1, which is equal to 1 upon 0.85 square minus 1. If you solve this, this thing will give you 0.3841. Okay, and in similar way, we have this d2. This is equal to 1 upon delta 2 squared minus 1, which is equal to 1 upon delta 2 is 0.15 square minus 1, and this thing comes out to be 43.4444. So now we have this d1 and we have this d2, and we have omega ls and omega lp from the previous question. So we have the sufficient information required in order to find our order. So let us substitute it. So we have this n, and let us take the least possible value of order, so we can just replace it by equality. So this thing here will be half of log of d2 is 43.4444 by 0.3841 divided by log of omega ls. Omega ls we found out as 1.3929, and omega lp we had mapped to 1, so this will be 1. Okay, so we have this thing here. So now we have half of this log of this quantity here will land up to 2.05484844, and the one in the denominator will give me 0.14373282, and this will give me, after simplifying, 7.1482 and this will be equal to 8. So the minimum possible value of order is, so basically we have this n to be greater than or equal to 8, and if we take minimum value, just keep it like this only, of n, then my n will be equal to 8. Any questions here? Is this clear? Is this part clear?
Okay, madam.
Yeah. Okay. So now we have the order. Now what we need to do is we need to figure out what is the cutoff frequency that we can use. So we know about the range of cutoff frequency, so that we can figure out. So what we can do is we can figure out the range of cutoff frequency. We know that this omega c should be less than or equal to omega ls upon d2 to the power 1 by 2n, and this should be greater than or equal to omega lp upon d1 to the power 1 by 2n. We know we had figured out the value of all of these factors. So now let us take this thing first, or let me just write it directly. So this omega lp is mapped to 1, and d1 we had found out here as 0.3841. So let me substitute here. To the power 1 by 2n, and 2n is 2 into 8, that is 16, which is less than or equal to omega c, which is less than or equal to omega ls we had found out as 1.3929 divided by d2. d2 we had found out as 43.4444. So this thing will be 43.4444 to the power 1 by 2n, which is simply 16. And if you simplify this, we get as 0.9419 less than or equal to omega c less than or equal to 1.2658. So we can take any value of omega c that lies between these ranges. Okay. So we have this here. Now the next thing that we need to, another part of the question is further find the filter transfer function. So this filter transfer function, we saw that it is h analog of s, which is equal to omega c to the power n upon product of k running from 1 to capital N s minus sk, and for our case this will be omega c to the power 16 divided by product of k running from 1 to 16 s minus sk. And since it is a Butterworth filter, we have sk as omega c into e power j 2k plus 1 plus n by 2n pi. So this comes out to be omega c into e power j 2k plus 9, n is 8, so I am substituting n as 8 here upon 16 into pi. So these are the values of sk's that I am having, and this k I shall vary from 1 to 16. And what values of k we will take? Allowed values are for k running from 1 to 8. Okay, those lie in the negative, in the left half plane of hs. Okay, so now we can substitute this thing. So I can write this in a simple way as omega c into e power j 2k plus 9 by 16 pi. So therefore h analog of s is equal to omega c to the power n upon product, this is 16, k running from 1 to 16 into s minus sk is omega c into e power j 2k plus 9 by 16 pi. Okay. Now what should be the next step here? So basically what have we obtained? This H analog of S, what is this quantity? This is basically a low pass filter. Right. So now we need to convert it to our required band pass filter. So we need to convert, or rather transform, to band pass filter. Okay, and that transformation I can do by replacing S with S square plus omega naught square upon Bs. Okay, this substitution I should do. How can I say that this substitution is correct? So if I say that this is j omega L, so this thing I should replace by S is j omega, so minus omega square plus omega naught square upon bj omega. So this j I can take up, so minus 1 by j will be j omega square minus omega naught square upon b of omega. So this is exact transform which we had used in order to do the mapping thing, whatever we had done earlier. So is this part correct? Is this part clear to everyone? So now we had this low pass filter. So basically this was SL, this was SL. So we have this low pass filter. Now we need to do this low pass transformation. So we need to replace this SL with S square plus omega naught square. What was my omega naught square? So this omega naught square we had found out here. Yeah. So this was the omega naught square, which is 1.6783. Divided by this B was bandwidth, which we had found out in the same part as 0.5161 S. Okay, so now let us substitute this in this expression. So now we'll have H analog of S, and this is for, let's say, band pass filter which we require. This will be omega c to the power 8 divided by product of k running from 1 to 8. I write 1 to 16. This is 8. Yeah. Now this S should be replaced by S square plus 1.6783 upon 0.5161 S minus omega c into e power j 2k plus 9 by 16 pi. So now I can write this as omega c to the power 8 into 0.5161 s to the power 8 divided by product of k running from 1 to 8 s square minus omega c into 0.5161 s into e power j, or let me just write this. Let's just write this part as sk just for brevity. So this will be sk into 0.5161 s plus 1.6783. So this is the analog equivalent. Now what do we need to do next? Next step will be doing bilinear transform. So after that, final step, do bilinear transform. That is, replace this S by 1 minus Z inverse upon 1 plus Z inverse. Okay, so this was H analog of S. This we had. So H of Z will be equal to omega C to the power 8, or rather I can write this as omega C into 0.5161 to the power 8 multiplied by 1 minus Z inverse upon 1 plus Z inverse to the power 8 upon product of k running from 1 to 8, 1 minus Z inverse upon 1 plus Z inverse square minus 0.5161 sk 1 minus Z inverse upon 1 plus Z inverse plus 1.6783. So if you simplify this, you will get the final answer for this question. So let's stop here. Let's not figure out what are the final things.
Madam, on the
Yes, sir.
hello, madam.
Yeah,
Uh,
please ask.
0.5161 S to the power 8. Correct, madam? Is it correct? To the power
Yes,
8.
yes.
So because there is 5 multiplications are there, so 8 you will get. So 8 are taken out.
Here, this was in bottom, right?
Yeah, yeah.
So this is 0, this 0.5161 is getting multiplied with itself 8 times
Yeah.
since it is running from K to 1.
Okay.
So
Okay.
that's why this is in denominator to the power 8. So that's why I can just put it in the numerator. Is it okay?
Okay.
Any other questions? Okay, if there are no questions, let me just quickly go like skim through whatever we have done today. Like whatever we have done in this particular till these questions, like from yeah, for this particular set. This is for Butterworth. We'll have 2 questions for Chebyshev also, but it won't be that rigorous. But just to give a glimpse of filter design, so these were the specifications given to us. Like we had been given what kind of signal we have, then tolerance we have been given for passband and stopband. They gave us the sampling frequency. We had our passband and stopband edges given in kilohertz, and we had the sampling frequency as 330 kilohertz uh, given to us. So in order to do, the aim is to design a band pass filter, a digital band pass filter, or rather a discrete time band pass filter. So for that, we did some steps. So the first step that we did was we found out the normalized specifications. So if I have FP, FS, FP1, FP2, FS1, FS2 in analog frequency domain given to us. So first step we'll do is we'll find out the normalized specifications by using this formula, which is omega as 2 pi f by sampling frequency. So if we use that formula, we'll get a set of normalized specifications as omega p1, omega p2, omega s1, omega s2. Okay, so this normalized specifications are basically specifications in terms of angular frequencies for the digital filter or the discrete time filter. Okay, once we have these specifications, the next thing that we will do is we'll convert these back to analog equivalents, or we'll unnormalize it by using bilinear transform. So bilinear transform give us a relation between omega and omega by 2, and this relation is omega equal to tan of omega by 2. Okay. So this omega p1 will give me a capital omega p1, which is unnormalized frequency. Similarly, this omega p2 will give us capital omega p2, which will be unnormalized frequency. And similarly, we'll have the unnormalized frequencies for stop band edges also. So now we have omega p1, omega p2, omega s1 and omega s2 all capital, and these are basically the specifications of the band pass filter in the analog domain. Now these first two steps have to be done for any kind of filter which is asked you to design. For example, if you are given a low pass filter, you will have a band pass and band stop per edge. Same process you will have to repeat for your band pass and your band stop edge. Okay. You will have to do a normalized, you will have to find out normalized specs, you will have to find out unnormalized specs. If you have to design a low pass filter, then this is what you require. Now, if you are given a band pass filter, band stop filter, or a high pass filter, then in that situation, you need to do one additional step, and that additional step is converting that filter or transforming that filter which you have found out, or filter specs which you have found out in previous, let's say we had band pass filter, to its equivalent low pass filter, and we need to do the equivalent frequency mapping. So for that, for our given case, we had a mapping of omega p to 1, and since it was a band pass filter, that mapping is given in this form, which is something like this. And in order to find, now we want a low pass filter, and a low pass filter has a single stop band edge, but this band pass filter will give me two stop band edges. So which one should we choose? We want to design a good filter, so we should choose that particular cutoff frequency which will give us a tighter constraint. So tighter constraint means we should go for a lower side of stop band edge. So what I mean is, this is my low pass frequency, low pass filter. This is my omega p, or rather omega p, and this will be my omega s. So if my omega s is small enough, if my omega s is small, this transition width will be low and I'll have a better filter. So that's why I'll go for a tighter constraint to design a better filter. That's why I'll take minimum of these two, but in magnitude. Okay. So for that, the formula is given here, and we'll make use of this formula to find out the mapped frequencies for both the stop band edges, which come out to be like this and like this, and we'll take minimum of them in magnitude, which came out to be something like this. Now we have omega LP, which is cutoff frequency for a low pass equivalent, and we have omega LS, which is again the omega LP, the pass band edge of low pass equivalent, and we have omega LS, which is stop band edge of the low pass equivalent. Okay, now once we have this is sufficient information to find out order. Now this step is, again I mentioned that this step is specific only when you are given to find out any filter other than low pass filter. If you have to design a low pass filter, you just don't need to do this particular step, and you can directly jump to this step where you need to figure out what is the order of the filter. And for the given filter, which was Butterworth, this was the formula of the order. Based on the stop band attenuation and pass band attenuation, you can figure out this D1 and D2 values and substitute back in this order equation. And this order equation, when we solve, we get a particular value of n equal to 8. This is again the standard process you need to figure out. Okay. After that, once you have an order, you can find out the range of cutoff frequency using this particular formula. And after you find the cutoff frequency, you can select any value of cutoff frequency in that particular range, and that can be and then we can find out the transfer function, which is given by this formula. So if we be very specific, this particular formula is for low pass equivalent, and this low pass equivalent will have n number of poles.
Madam,
Yes.
here you mentioned n, no, but replace with 16. Omega c to the power n.
Sorry.
Here also, denominator.
Okay. And okay, so this transfer function has sk here, and this sk is, any other question? Okay. Okay, so this sk is omega c into e power this particular formula. After substituting, we get something like this. So this H analog of S is given by this particular formula. As I mentioned, this was a low pass filter. We intended to design a band pass filter. In order to get this band pass filter, we need to do this analog domain transform, which is given by this formula here. So once we do that, we'll get the analog thing for our for our band pass filter. But this is still an analog filter. After that, we need to figure out, or we need to do bilinear transform, where we need to replace this S by 1 minus Z inverse upon 1 plus Z inverse. So after doing that, you will get the actual H of Z. Do you want me to summarize these steps in a form of a list here? I have time, I can do that. The remaining two questions are simple enough. I can do that. I can just list down the steps one by one. Do you want me to do that, sir?
Do it, madam.
Okay, yeah, fine. So let me, so steps for filter design, specifically digital filter design. So what is given to us? We have specs in analog domain. This includes pass band and stop band edges and tolerances, and importantly sampling frequency. Okay, this is given to us. Now let us start with step 1. It is find normalized specs, and for that you will use this formula. Omega is 2 by f by f sampling frequency. After that, once you have this formula, then you will do step 2. Find unnormalized specs using bilinear transform. So this you will do by using the formula omega as tan of omega by 2. So this will give me specs of equivalent analog filter. Okay, then we have step 3. This is analog transform, and this thing is for high pass, band pass, and band stop filters, and we need to ignore this step if filter is low pass. Okay, so here what we will do is we will map omega p to 1, and we'll figure out what is omega s or LP and omega ls, figure out using analog transform specific to the given filter. Okay, so this analog transform for high pass is omega L as minus omega P by omega, and for band pass it is omega L to be replaced by omega square minus omega naught square upon omega naught into omega into B, where omega naught is, or omega naught square is omega p1 omega p2, and B is omega p2 minus omega p1, which is bandwidth. So now you have omega lp and omega ls. This was step 3. After this step 3, you will do step 4. So step 4 is construct a low pass filter, or rather we'll find order n of the low pass filter using omega ls and omega lp. Any questions?
Madam, in step 3, you have to write for band stop also, no? Band stop filter.
Band stop is not yet covered, sir. That will be covered
Okay,
in next
okay,
week. Yeah.
okay.
Okay. Step 4 is this. Then we need to find low pass filter, order of low pass filter. Step 5 is find the cutoff frequency omega c. So basically take any value in range of omega c. So now we have omega c and omega s, omega c and n. Next step is step 6. Construct the equivalent low pass filter analog transfer function, which is basically H analog of S, and this will be specifically for low pass. So this transfer function will vary based on whatever filter design you are doing. Then you have step 7. So in step 7, you will do analog transformation. Again, this will be for band pass, band stop, and high pass filter, and need to ignore this step for low pass filter. So here you will replace this SL with omega p by S for band pass, for high pass, and you will replace this LS with S square plus omega naught square upon BS for band pass. For band stop, it will be discussed in coming lectures. So this will give us transfer function. Let's say H analog of S for desired filter. Okay. And now we have the last step, that is step 8. And this step 8 says that we need to do bilinear transform. That is, we need to find out H of Z, which will be equal to H of analog of S, where S we need to substitute as 1 minus Z inverse upon 1 plus Z inverse. So basically what we need to do is we need to write this or replace this S by 1 minus Z inverse and 1 plus upon 1 plus Z inverse and simplify to get the transfer function. So these are the steps for designing the filter. I have listed it down so that it will be helpful for you to solve your assignments and other things. Is it clear? Okay. If there are no questions, then let me move on to the 9th question today. Okay. So now the 9th question says that for a Chebyshev filter, find the maximum value of epsilon. Okay. So in this here, cutoff frequency and other specs, let me add it. So now we need to find out what is the maximum value of epsilon. So we know that for a Chebyshev filter, this epsilon can be at least equal to under root of d1, and d1 we had found out. So this d1 is 0.3841. So this thing here is under root of 0.3841, which comes out to be 0.61975. So this epsilon is less than or equal to 0.61975, which means that maximum value of epsilon is 0.61975. Okay, simple. Any questions? Yes, sir.
Madam, what is the importance of this epsilon? Because in order also D1 will be there. It is the only subset of D1. What is the importance in Chebyshev filter?
So in Chebyshev filter, you have this thing like oscillations you have, right? You have ripples. You have ripples. It is an equiripple in passband. So that ripple thing, that will be controlled by this epsilon.
No, epsilon is a derived parameter, no, madam. It's the under root of D1, no?
Huh.
Why is that specifically it is mentioned as a single parameter?
Now this ripple thing comes up in passband, right? So, and this D1 is passband tolerance. That's why it is just related to D1.
Okay.
Does it answer your question?
It's okay, madam.
Okay.
Madam,
Yes.
I think this epsilon is also useful for even order filters for Chebyshev. If it is even order for omega is equal to 0, the response will be at omega is equal to 0 is 1 by under root 1 plus epsilon square.
Huh.
So, depending on the order, epsilon is useful.
No, epsilon is useful. It is a control
Yeah,
parameter for that filter.
yeah,
It is an
yes,
important parameter that actually defines the Chebyshev filter.
yes.
It is giving you your height of your ripple in your passband, and it is giving you how it will fall off and other things. Everything it is controlling. It's a very important parameter, and this is introduced just to characterize that ripple thing, so that Cn like cosh and this thing and Chebyshev polynomial along with this basically controls everything. So it's a very important design parameter. However, in Butterworth filter, we don't have ripples and other things. So it is very simple to design compared to this.
So, in getting the constant in the Chebyshev filter, we have to equate the response to equal to k at omega is equal to 0. So, to find out that constant, epsilon is very much useful.
Yes, yes, it is useful.
Yeah,
It is
yeah,
useful. It
yeah,
is useful. It is important.
yes. So, so,
It is a filter parameter. So you need to find it out. Okay. If there are no further questions, let me just move on to the last question today. So we need to find the minimum possible order for the Chebyshev filter for the given specifications. So for Chebyshev filter, this order n is greater than or equal to ceiling of cos h inverse of under root of d2 by d1 upon cos h inverse of omega ls upon omega lp. So this order thing is to be found out for low pass equivalent. Okay, now if we go back, we had found out this D2 as 43.4444. This D1 we had found out as 0.3841. This omega ls is equal to 1.3929, and this omega lp we had mapped to 1. Okay, so now if we substitute it here, we have this n to be greater than or equal to cos h inverse of under root of 43.4444 upon 0.3841 divided by cos h inverse of 1.3929 divided by 1, and if we use calculators, this comes out to be 3.0551 upon 0.8597. This comes out to be, let me just add another page, it's too much crowded. Yeah, so this n what we have is greater than or equal to 3.0551 upon 0.8597. This comes out to be equal to 3.5537, which means that this will be equal to 4. So minimum possible order is equal to 4. Is it clear? Any questions here? Any questions in this particular part? Or any question in today's tutorial? This was the last question that I had planned to cover today. If you have any questions, please let me know.
Madam, no questions on tutorial.
Okay.
But we are having some doubts regarding the assignment 7.
Which assignment, sir?
Assignment 7, which was
This week
already
assignment.
evaluated. Yeah, already evaluated now.
Already evaluated. Sir, assignment related queries, I am not the in charge of it. Actually,
Our problem is we are not getting the proper solutions. They are mentioning solutions, but we are getting just like ABCD, and they are not giving the proper answers. We need solutions, no, madam.
I
Justify.
understand,
Yeah,
sir, but
yeah.
it's
And
actually not.
okay,
I
madam, but
can't do
you are only,
anything in that.
yeah, madam, you are only our point of contact. They are not at all listening. They are not bothered.
Oh,
And
okay.
partial marking is there. We know that. Suppose if A, B, C are correct, we gave A, B, but other one we gave wrong. They have to give
Huh.
partial marks, no? Even that also they are not doing.
So partial marking,
And,
it was there earlier, right?
but they are not giving. In some assignment they are giving, in some other assignment they are not doing. It is not proper. So we are not having proper persons to contact.
See, this
Is
assignment
yeah.
thing, like multiple answer thing, if I'm not wrong, this thing might be an issue from NPTEL end. So you can just mail to NPTEL person who handles, or some NPTEL contact if it is there for helping kind of thing. So you can write there. And for solutions for assignment, it's only the, like
They are not proper, madam.
I
Yeah,
can also
yeah.
contact only through that portal. I also can't contact them directly.
Mm.
So even I'll have to
Mm.
put a request on that contact
Yeah,
portal
yeah,
only.
madam.
Yeah.
Whenever there are some trivial questions, they
Huh.
are giving partial answer, even that also partial answer. Finally, they are suppose something is there, some answer we have to get,
I
some
understand.
equation multiplied with h of e power j omega plus some other equation h of e power minus j omega. Then they are leaving. They have to find out h of e power j omega also. No, then only we can understand. Like that,
Okay.
they are not. They are giving partial answers. Even if full answers are given, in that also they are giving partial answers.
Okay.
Yeah, that is what we are getting. That is
Yeah,
the
I'm
trouble we are getting.
understanding what you're saying.
Yeah, yeah, yeah. From the beginning, same trouble.
Yeah, I'm.
Yeah. Mm.
No one pointed out in the session. Like there were
Yeah,
two, three
yeah,
people. No one pointed out, and like,
yeah.
yeah, okay. What can you do? Have you posted it on portal again? Because I don't know if they'll reply or what they are doing.
They will change the marks. So far, nothing is done. Assessment also they have to change, no, madam, according to the troublesome questions. They have not done.
Oh, okay.
Yeah,
But they will do it before the final exam mark calculation.
yeah, they
Because
have to
I
do. No,
saw the reply to that particular mail, that I have seen that they'll reassess it. But yeah, you
but they
can
are
just
not
put a
doing, madam.
gentle
Yeah,
reminder on that. I really can't do anything.
yeah,
I
yeah.
really
Okay,
can't do.
understood, madam. But we can't express anywhere. That's why we are expressing before
I
you.
understand, I understand.
Yeah,
The least thing I
yeah.
can do is, like, in this week I didn't open the portal because I was loaded with multiple things.
Okay.
Least thing I can do is the question which you feel is too difficult to understand, na, just point
Yeah.
it out at least 2 days before this session, so that I'll add that in my presentation, and I'll discuss its solution of the
Okay.
solution of that questions whose solutions are released. So that assignment
Okay.
of solutions are released. That I can do.
Okay.
Yeah,
Okay.
that much I can definitely do. Yes, sir.
Are you hearing me?
Yes, sir. Please ask.
Madam, in the same assignment, there are two trivial questions. In the two trivial questions also, solutions are given just like answers only, options only, but not reasoning is not given. For example, designing of the Chebyschev, your Butterworth filter, they have given it is a sufficient condition, but it was went wrong. I don't know why it is went wrong. That reason it is not given. And one more is bilinear transform. Bilinear transform is about 1 minus as you are telling, S is equal to 1 minus Z inverse by 1 plus Z inverse. One counter example is given, and answer is given that counter example is student is wrong. Some other counter example can be taken like that. But for those two, the justifications are not at all given.
Okay, sir, please do one thing. Just put the
I
question number in the portal. I'll solve this in next tutorial. Definitely, I'll solve it in next tutorial.
okay. The only that yeah, I'll put the questions to you, madam.
Yeah. I'll
Because
solve
at
it in
the
next tutorial, or I'll at least mail you the solution. That I'll definitely do. If the next
okay,
tutorial
okay.
is too long, I'll mail you the solution, detailed one. That I'll do.
Okay.
Okay. Yeah.
Thank you.
Any other questions? If not, then that was all from my side today. Yeah. Yes, sir. Any questions?
No, madam. By mistake it come.
Oh, okay. Yeah. Okay. Thank you for attending today's session. If you have no further questions, please, you're free to leave the meeting. Thanks again.